Welcome back to Algebra, and in fact to the very last video of this series. And in this video we're going to use the Sylow Theorems. We're going to learn how to use the Sylow Theorems for our goal. Remember that our goal all this time was to classify groups, classify finite groups. And we have done so. We have actually proved, have done it for finite abelian groups. The fundamental theorem of finite abelian groups told us that if it is finite abelian, then it is isomorphic to a product of cyclic groups of prime power order. So we know exactly what are all the possibilities for finite abelian groups. And now it remains the very big question, very big project that we're not finishing here, but what happens with finite non-abelian groups. And to that goal, we are going to be able to prove a couple of things today using Sylow groups. By the way, we did prove one thing. We have proved along the way using group actions and the class equation. We proved, for example, that every group of order p squared for p prime is abelian. So that helps me understand already between things that we know already about abelian groups and this result, it helps me understand a lot of different groups. Let's see what groups we can understand with that, with those two statements. We have groups of order 1, that's the trivial group. Groups of order 2, we also have, like from basics, we actually have that every group of prime order is cyclic and therefore abelian. So a group of order 2, we know groups of order 1, groups of order 2, we know those are cyclic. Groups of order 3, that is cyclic. Groups of order 4, those have to be not cyclic but abelian because it's a group of prime square prime order. So those we understand. Those are the possibilities are either z modulo 4 or z modulo 2 cross z modulo 2. Then we have groups of order 5. That's prime. Done. Groups of order 6. What about groups of order 6? For groups of order 6, we now already have a choice. It can be, there's two different groups, and one can show that they are either, well, it can be z modulo 6 by the classification of abelian groups. Every group of order 6 that is abelian is z modulo 6, or it can be S3. And in any case, you can keep going like this until you get, for example, to orders like 15. What happens with 15 now that is 3 times 5? And we're going to see, well, we don't know anything yet that covers that case, but we're going to prove a result today that helps us uncover what's happening with groups of order 15. And the group theorem that I want to show today is the following, which is going to be an application of the Sylow theorems. So here is a theorem about groups of not prime power order, but the order is going to be a product of two primes. So let P and Q be distinct primes with, let's say, P less than Q, and let G be a group of order PQ. Then the following happens. One, G has a unique subgroup of order Q, and it is normal. Is normal in G. And 2, if Q is not congruent to 1 modulo P, then there is also a unique subgroup of order P, of order little p, and it is also normal. And more importantly, G is cyclic and isomorphic to Z modulo PQ Z. So let's see a proof of this, and you can see that this is very strong. It's telling me that, for example, let's see an application right away, that if G is of order 15, then this is, because 15 is 3 times 5, here P would be 3, Q would be 5, and Q5 is not 1 modulo 3. 5 is in fact 2 modulo 3, and therefore every subgroup, every group of order 15 has to be cyclic of order 15. So there is no non-abelian groups of order 15. They are all abelian, and they are all cyclic of order 15. So this is very strong, very nice. So let's see how you prove this using Sylow theorems. So here's the proof. Suppose G is of order PQ and P is less than Q for now. Then by the first Sylow theorem, there is at least one subgroup Q of order exactly Q. Here P and Q are primes. So the Q, which is a Q Sylow subgroup. And well, we have also the third Sylow theorem tells me how many of these are there. And the third Sylow, this is Sylow theorem, tells me that NQ, which is the number of Q Sylow subgroups, satisfies that it has to be 1 modulo Q, and NQ divides the order of the group, which is PQ. So this gives me two things. One, it has to be a divisor of PQ, but there are very few of those. It has to be 1 or P or Q or PQ. And 2, it has to be 1 modulo Q. So NQ is 1 plus Q times K for some integer K. And then you can see right away that Q itself is not 1 modulo Q, so it cannot be Q. PQ is 0 modulo Q, so it cannot be PQ. It could be 1 or it could be P, but P is, if suppose that 1 plus QK was P, P is less than Q, and that would be automatically a contradiction, because if K is bigger or equal to 1, then this would be bigger than Q, and that would be a contradiction. So that tells me that NQ cannot be P, and therefore NQ has to be exactly 1, which tells me the upshot of that is that Q is unique. And then the second Sylow theorem tells me that Q actually has to be normal in G, because remember that all the Sylow subgroups or the Q Sylow subgroups are conjugates to each other. So if there is only one, when I conjugate Q, I have to get Q back, and therefore Q is normal in G. So that is a consequence of it. Okay, so Q is normal in G. Maybe I should state that separately as a theorem, the fact that this is a consequence of the second Sylow theorem when we have a unique Sylow, but in any case, I will do that in a moment. Let's finish this proof first. So this is what happens if I just know this. There's a unique Q Sylow with the larger prime. There's one unique Q Sylow. So let's see what happens with the P Sylows. Okay, so the second part of the theorem is the following. Suppose G is PQ, P is less than Q. That alone has told us that there is a unique subgroup of a unique Q-Sylow subgroup. And now let's also assume that Q is not 1 mod P, and let's look at the P-Sylow subgroups. So again, the first Sylow theorem tells me that there is a P-Sylow subgroup. So there is a P-Sylow of order P. And the third Sylow theorem now tells me that NP is 1 modulo P, and NP divides the order of the group, PQ. So this tells me that NP is 1 or P or Q or NQ, and this tells me that NP is 1 plus PK with K some integer. Okay, so what can we deduce? Right away, if NP is 1 modulo P, it can be 1. It cannot be P, and it cannot be, this was supposed to be PQ. So it cannot be PQ because that is a multiple of P. That is not 1 mod P, that's 0 mod P. And the other possibility is that can it be Q and NP is not Q, because if NP was exactly Q, then Q would be 1 plus PK, and that would imply that Q is congruent to 1 modulo P. But that is a contradiction because we have assumed that Q is not 1 modulo P, so it cannot be a Q either. So it is not Q either, and therefore NP is also 1, and therefore there is a unique P Sylow. There's a unique P Sylow, and therefore by the second Sylow theorem, I'll state that separately in a moment, that tells me that P is also normal in G. Great. So what do we have now? I have that also, I have a unique P Sylow, I have a unique Q Sylow, and they're both normal in G. So how can I conclude that G is cyclic? So to recap, we have G is of size PQ, and we have unique subgroups P that are normal in G, Q that is normal in G, with the size of P being exactly P, the size of Q being Q. Those are the corresponding P Sylow and Q Sylow subgroups of G. The last piece I need is that these are actually, the intersection of the subgroup P and Q is actually trivial. So I'm going to prove that Q intersects P is actually just the identity. For that claim, let G be in Q intersect P. Then, well, on one hand, G is in Q, and as a consequence of Lagrange's theorem, let me write it here since it's another one of these big theorems that we've proved in this class. As a consequence of Lagrange, what we have is that the order of G divides the order of Q, which is Q. So the order of G divides Q. And G is in P, and similarly, the order of G divides the order of P, which is P. And the only number that divides P and Q has to be a number that divides the GCD. It divides the GCD of P and Q, which is 1 because they are distinct primes. So therefore, G itself is identity, and I've proved my claim. Why am I done? I am done because in the previous video to this one, I proved a theorem that actually has my favorite proof in all of abstract algebra. You can see it in that other video, which says that if we have G with P normal in G, Q normal in G, and P intersect Q is trivial, then the elements in P and the elements in Q commute. Any, let's say, G1 in P and G2 in Q commute. So G1, G2 is G2, G1. And how am I going to use that? I'm going to use it as follows. Since P is of size P, and that is prime, P itself has to be isomorphic to Z modulo P. So it is generated by one single element. Let's call it G, okay, with G of order P. And since Q is Q, I have an element that generates Q, let's call it H, with order exactly Q. So what is the order of GH? Well, notice that GH to the PQ, since G is in P and H is in Q, they commute by my favorite theorem over here. They have to commute with each other, and therefore GH to the PQ is the same as G to the PQ times H to the PQ. And here I'm using the G and H commute. Okay, that's very important. That's not true in general. But now G to the PQ, the order of G is P, so this is G to the P to the Q by the loss of exponents, and this is G to the Q to the P by the loss of exponents, so this is E times C, so this is E. Therefore, the order of GH is, it divides PQ, and it is not P or Q because GH to the P would be G to the P, H to the P, which is H to the P, and the order of H is Q, not P, so this is not identity, and the order of G to the GH to the Q is G to the Q, H to the Q, which is G to the Q, and the order of G is P, so this is not the identity. And so all these three things together tell me that the order of GH is exactly PQ, which is the order of the group, and therefore I have that G is cyclic, is generated by all the multiples of GH. So G is actually generated by GH. I found a generator, and it is isomorphic to Z modulo PQ cyclic, which is what I wanted to prove. As promised, let me state as a separate result the following. Let G be a finite group, and let P be a prime such that P divides the order of the group, and there is unique we know there is at least one p Sylow subgroup, but suppose there is a unique p Sylow subgroup of G, then P is normal in G. So here's a proof. Let P be as above, and let G be some element in G, and consider H, which is going to be a conjugate of P. By the second Sylow theorem, we know that every conjugate, every other P Sylow has to be a conjugate of P. And in fact, every conjugate of P is also a P Sylow. So that's something that I can prove right now, which is as follows. So consider this other conjugate. And first note that the size of H is the size of the group GP G inverse, which is how H was defined. But also, we have actually seen that a conjugate subgroup has the same size as the group itself. So this has the same size as P, which would be something like P to the R, where, because it is a P Sylow, the size of G has to be P to the R times M, with P not dividing M. But that means that H itself has the size P to the R, which makes it, by definition of P Sylow, also a P Sylow. So H is another P Sylow of G, but there are only one. We are assuming that there's a unique P Sylow, that NP is 1. So NP being 1 implies, so that is what this condition says, is that NP, the number of P Sylows, is exactly 1, then H has to be P. Hence, what I've just shown is that for all G in G, we have that G, P, G inverse, the conjugates of P, is exactly P, and therefore that is one of the equivalent definitions of normality. So P is normal in G, like we wanted to show. So this is the fact that I've used a couple times in the previous proof. Okay, let me just do one last example that is going to be similar to the theorem we've proved, but not exactly the same. But the method is going to be exactly very similar to prove another classification result of groups. Let's, as an example, again, of usage of the Sylow theorems, let's do the following. Let's classify all groups of order 99. Okay, so we're going to proceed in a very similar way as we did before. So let's start with G is of order 99, which is 9 times 11, so 3 squared times 11. Let's start with the 3 Sylow subgroups. So take P to be 3. Then by the first Sylow theorem, we know there are 3 Sylows. Every 3 Sylow has order 9. And the third Sylow theorem tells me that the number of 3 Sylows has to be 1 modulo 3. And N3 has to divide the order of the group. Since the order of the group is 9 times 11 and has to be 1 modulo 3, so I'm only going to look at divisors that are not divisible by 3. So, or if you want, what are the divisors of 3 squared times 11? Well, there is 1 and 3 and 9 and 11 and 33 and 99. That's it, right? 11, 33, 99, yeah. So those are all of them. And now I consider this this condition. It cannot be 3. It cannot be 9. Those are 0 modulo 3. it cannot be 33, and it cannot be 99. And 11 is 2 modulo 3, so it cannot be 11 either. So it has to be 1. So this tells me the upshot is that N3 is exactly 1. There is exactly 1 3 Sylow subgroup. And by my previous result, that means that there is a unique 3 Sylow, and it has to be normal in G because there is only 1. Great. So now what about the other prime divisor? By the way, this is a 3 Sylow, so I know that the size is 9. Great. What about 11? Again, and 11 has to be 1 modulo 11, and 11 has to divide 3 squared times 11. So again, if you write all the possible divisors, now it cannot be 11 because it has to be 1 modulo 11. It cannot be 33. It cannot be 99. Those are all multiples of 11, so those are not it. And it could be 1, sure. 3 is not 1 modulo 11, and 9 is not 1 modulo 11. This is 3, this is 9 modulo 11, so those are not it. So it has to be 1. So I also have that the number of 11 Sylows is 1, so there is a unique subgroup which is also normal in G, and it is unique of order 11. And finally, now also note that these 3 Sylow and the 11 Sylow have to have trivial intersection because something in that intersection, the order of the group would divide the size of P3, which is 9, and the order of the group would divide 11. So the order of the group divides the GCD of 9 and 11, which is 1, and therefore G is 1, or meaning that G is the identity. So their intersection is trivial, and therefore by my theorem with my favorite proof, we have that the elements of P3 and P11 commute. Okay, but that doesn't mean that this group is going to be cyclic, because now I don't necessarily have a generator for P3. However, I do have the fact that P3 has order 9, and therefore it is abelian. And I know by the fundamental theorem of the classification of finite abelian groups, P3 has to be abelian, and it has to be either cyclic or 2 copies of Z modulo 3. And now I have one more result to use here. The last bit I need to put everything together is the following. I'm going to consider H. It's going to be a subgroup of G, and it is, well, G times H, where G is in P3 and H is in P11. That is a subgroup, and this is a subgroup of order 9 times 11. Is of size 99, which is the same as the size of G. So actually what I get is that H is G. And what else do I know? I know that the elements of P3 and P11 commute. I just found out that G is the product group. And we have also proved that the intersection is trivial, but these are precisely the conditions for G to be a direct product, an internal direct product of those two groups. So G is actually isomorphic to the 3 Sylow direct product with the 11 Sylow. And now, since the 11 Sylow, by the way, is of order 11, that implies that the 11th Sylow has to be cyclic of order 11, and we have found out there are two possibilities for the 3 Sylow, and that tells me everything now I need to know, that G is abelian, and it has to be isomorphic to either Z modulo 9 cross Z modulo 11, which by the Chinese remainder theorem, this is actually isomorphic to Z modulo 99, or it is Z modulo 3 cross Z modulo 3, that is the 3 part, the P3, the other possibility for the 3 Sylow, times Z modulo 11Z, which can be simplified just a little bit using the Chinese remainder theorem to be Z modulo 3 cross Z modulo 33Z. So these are the only possibilities for a group of order 99, is that it has to be abelian and it has to be isomorphic to one of those two groups. So this is one way in that you can use the Sylow theorems to classify, for example, groups we've classified today, groups of order 15, groups of order 99. This is not enough, though, to classify groups. For example, if you go to 21, so in order 21, you do have that 7 is 1 modulo 3, so the theorem we proved does not apply, and there are other non-abelian groups of order 21, which can be constructed using what we call semi-direct products, which is a topic that's usually taught in a second course in abstract algebra or a graduate level course in abstract algebra. So I hope you go on and study more group theory and abstract algebra. If you're going to do so, I would suggest that you invest in a book called Abstract Algebra by Dammit and Foote, which is a fantastic resource for algebra at the graduate level. So anyway, that's it for this course, and maybe you will see me in some other video series on some other algebraic number theory topic of some sort. So until then, bye bye.